Alright, I'm back with the start of page 3. This is number 12. Solid object floats in water. Again, it floats, so we know that Fg and Fb are equal. It says 3/4 of its volume is beneath the surface, so we know the specific gravity is 0.75. What is the object's density? It's 750, because specific gravity is rho of the object divided by the rho of water, which is 1,000 kilograms per meter cubed. So if this equals 0.75, cross multiply and you get 750 kilograms per meter cubed. Pretty simple. Number 13, 4.7 kilogram solid sphere, so we know that's 4/3 pi r cubed if it's important. Made of metal whose density is, so m is equal to 4.7. Density is 4,000 kilograms per meter cubed. If you're wondering, I don't have my Apple pen or pencil. I have this crappy stylus, and that's why my writing's awful. But this is the best you're going to get out of me right now. This hangs by a light cord. When the sphere is immersed in water, what is the tension in the cord? This is very similar to the other question we did on the other side. So you have tension, you have FB, you have FG. They gave you the mass, so you know that's mg. FB, they don't give you the volume, but you can find it if you know rho and you know m. Rho is m over v, so v is m over rho. So we can find what v is. We can plug that in to rho vg because it's immersed. That volume of the object, whatever that is the same as the amount of the fluid that's displaced by putting it in there. So that's that. Rho is of water, G is G. Again, the similar idea with Newton's second law. We're going to say the tension plus Fb equals Fg. So the tension is, again, the weight minus the fact that the buoyant force is pushing up on it. You can plug in all the numbers and you'll get the answer that's correct. It's C 35 newtons, I think. Alright, next question. Number 14. Consider a very small hole in the bottom of a tank that is 17 centimeters in diameter and filled with water to a height of 90 centimeters. So this is one of the ones we did in class. This very small hole here, when you have a 17 centimeter diameter tank filled with water to a height of 90, so this height here is 90 centimeters. I guess it's in the, this hole was in the bottom, so there's your 90. Find the speed at which the water exits. We can do out the whole, Bernoulli's and say that V1 here is essentially 0. We want to know what V2 is. You guys all love shortcuts, so I'm just going to give it to you. It's radical 2GH. G 9.8H is that 0.9 meters is what you're going to want to plug in. That will tell you what it is, 4.2 meters per second apparently. Next question. This is number 15. Fluid flows at 2 meters per second through a pipe of diameter 3 centimeters. What's the volume flow rate? Volume flow rate is what our continuity equation is. It's A1V1. They give you the diameter, so the area is pi d squared over 4. Not sure where that comes from. R is d over 2, so when you square r, it's d squared over 4 times v. They give you the diameter in centimeters. The answers are in meters, so you better convert the 3 centimeters to 0.03 meters, and v is 2 meters per second. Do the math, you will get the right answer. It's D. It's so much easier and quicker to do this when you don't actually have to find the answer with numbers. I'm going to start doing this in class. Actually, I already do this. Alright, next question. Ideal incompressible fluid flows through a 4 centimeter diameter pipe at 1 meter per second. There is a 2 centimeter diameter constriction in the line. So you have a pipe, and then there's a constriction in the line. So it gets smaller, is all that means. What is the speed of the fluid in this constriction? Continuity says A1V1 equals A2V2. They give you the speed here is 2. the diameter is 3, but remember it's pi d squared over 4. On this side it's pi, the constriction is down to 2 squared over 4. Am I doing this wrong? Pi, what am I doing? Pi r squared, which is 4. Let me start over here. This is awful. A1 V1 equals A2 V2. Pi r squared times V1 equals pi r squared, this is R1, this is R2, over V times V2. So what's happening is essentially your diameter is being halved. If your diameter is being halved, the square factor there ends up being 1/4. So it's my drawing, the area here is 1/4 of what the other area was. For continuity to work, it has to go 4 times faster through there. So if it was going at 1 meter per second, now it's going 4 meters per second. Again, you can work it out in numbers. Next question, 17. Water, which can be treated as ideal and incompressible, flows at 12 meters per second in a horizontal pipe. That's important because the height isn't changing, and I'm assuming this is going to be a Bernoulli's question where you have P1 plus 1/2 rho V1 squared plus rho G Y1 equals P2 plus 1/2 rho V2 squared plus rho G Y2. If it's a horizontal pipe, these two numbers are the same, so you can get rid of those. They give you the speed at one spot is 12. And they tell you the pressure is 3 times 10 to the 4th. And it's water, so we know what rho is. So far so good. We got one side of the equation already set. If the pipe widens to twice its original radius, what's the pressure? So you want to know this pressure. The fact that the pipe widens affects what V2 is. If it is twice its original radius, the area is going to be 4 times. A2 is going to be 4 times. Continuity says that if the area doubles, quadruples, the speed has to be quartered in order for this to be equal to this. So basically your speed over here, if it's 12 on this side, it's now 3 on this wider side of the pipe. So I think you have all the information to be able to solve for what P2 is, and like I said the last time, you guys can do the math. Next question, 18. I think we did this one in one of the classes, and it's a lot easier than it might appear. The mass flow rate is what you're asked about, which is just, in units, it's kilograms per second. If you think about it in terms of dimensional analysis, you can take the density, which is kilograms per meter cubed, and multiply that by the volume flow rate, which would be meters cubed per second, and you'll get kilograms per second. And remember, the way you get the volume flow rate is the area times the flow speed. So this is how you get the mass flow rate. In the question, it's water, so you have rho. They give you the area of the pipe at C, do they? Yes, they get, and the pipe narrows to an area of 0.04 meters squared at point C. And do they give you V at C? Yes, they do. They give you V at C. So you have all of these pieces of information, so you can just multiply it out. I'm going to pause real quick. All right, we're on the last page. This is number 19. Looks like this is a little confusing drawing. It's 2 different size diameter cylinders, but it says they have a very light plate that sits on top of them. I'm not going to be great at drawing this. So the idea is it's all oil, it's enclosed, Pascal's principle is going to hold, so the pressure everywhere in here is equal. What we're interested in is how that pressure corresponds to forces. So in this case, they want to know how much mass should be placed on plate B to balance it. And the idea here is the force I guess this is B and this is A. So well, let me back up. Pascal's principle says P at A has to equal P at B. What I was going to do was jump into the F at A divided by the area at A equals F at B divided by the area of B. Again, this is by definition, pressure is force per area. So they give you the 125 kilogram is the mass of the object placed here, so there's going to be some weight that's equal to mg. Sorry, I'm screwing up with the program. So this is, when I say it was 125 kilograms times g divided by the area of A, which is pi times 0.175, I believe, based on the picture, if I'm seeing it correctly. That's r squared in meters. That's going to equal the mass times g that we're going to set on here. That's going to give you another weight that's going to balance it. And this is pi times, it's 10.2 centimeters, so it's times 0.051 squared. The g's go, the pi's go, so m is equal to 125 times 0.051 squared divided by 0.175 squared. It's not a factor of 3, but it's a little more than a factor of 3, or I guess a little less, 1 to something greater than 3. Square that, I don't know, like 1/9 of what that is. So I did the math. I trust myself. 10.62 is what I got. Next question. Number 20. An ideal incompressible fluid flows at a certain speed through a certain diameter cylindrical pipe. The pipe widens to a square. That's interesting. It doesn't say anything about, I'm just thinking in terms of Bernoulli, it doesn't say anything about heights, but let me keep reading the question. Assume steady flow throughout the system. What is the speed of the fluid through the square section? Okay, well, you don't even need Bernoulli's. A1V1 equals A2V2. Use continuity. What's weird is it's a round pipe going to a square. I don't think I've ever seen a square, whatever, square pipe. That's an awful drawing too. But I mean, you can find the area of a square just as easily as you can find the area of a circle. So set up A1V1 equals A2V2. Make sure your units match. It's given in millimeters for the diameter, so convert that to 0.044 meters. And it's a square, it's centimeters, so 0.055 meters. And it's just square that because it's a square pipe. This would be pi r squared, so you got to divide that by 2. So those are your two areas. V1, they tell you, is 0.252. That's going to equal whatever that area is times V2. I did it and I got 0.127 meters per second. Again, double check my work. The question B part of this is, what is the flow rate? So great, no Bernoulli's. In liters per minute. Liters per minute. That's interesting because we usually are doing this in, meters cubed per second. So we're doing it in slightly different units. The volume flow rate is just the A times the V, which we have all the numbers from the last one. Just pick the square one, 0.055 squared times 0.127 if you assume your answer is right, and you'll get a number that's meters cubed per second. Now what you want to do, again, it doesn't matter what that number is, you want to go from meters cubed per second to liters per minute. We're going to have to multiply by, well, there's 60 seconds in 1 minute. That was the easy one. How do we go from liters to meters cubed? 1 liter is 0.001 meters cubed. So whatever your answer was here, multiply by 60 but divide by 0.001. In my answers I put 1,000 liters are in 1 meter cubed. that's the same as that. And I don't know if you guys realize that's how many liters are in that. I mean, think of a meter stick by a meter stick by a meter stick. You know, that holds 500 2-liter bottles of soda, which is pretty scary. How much sugar is that? Never mind. All right, erase that. Last question. Oh, nice. The water tower that's elevated with a hole, and they want to know how far does it, what is it? How far is it traveled when it hits? So the water is going to spill out, and what is delta x? I should just not even do this, but I will. V equals radical 2gh. We can cheat and do that. Fantastic. I ended up with 14.4 meters per second. And then delta x you get from V initial and the x times t. This is V initial and the x, so we have that. That's good. We got to go find t. If you remember from kinematics, delta y will tell us the t. It's a horizontal launch, so V initial on the y times t is 0. We don't care about that. Plus 1/2 ay t squared. This is going to be negative, I can't read it, 8.75. This is going to be negative 9.8 t squared. The t that you're going to get, I think, is 1.34 seconds. Multiply that by that, and that will tell you how far it goes. And doesn't kinematics seem easy now that you're doing fluids? That's all I have for you. Good luck. And sorry I had to rush through this, but I have other things to do. All right. Night, everybody.